Welcome back. In this video, we're going to continue learning about intermolecular forces. Specifically, we'll talk about the intermolecular forces that exist when you have ions interacting with ions, ions with polar molecules, and polar molecules with polar molecules. Let's review what we saw already. We know that intermolecular forces exist between different molecules, that these are attractive interactions that hold those molecules together into groups. And because of intermolecular forces, we have macroscopic properties, such as the phases of matter, solid, liquid, and gas. Intramolecular forces are bonds. These could be ionic bonds or covalent bonds. And intermolecular forces are a lot weaker than intramolecular forces or bonds. And when we deal with intermolecular forces or intermolecular interactions, these interactions are temporary. So the electrons that are involved in those interactions are not permanently shared between the molecules. Intermolecular forces are due to electrostatic attraction. And we can relate the strength of the intermolecular forces to various variables. Typically, it's going to involve the charge on the species, whether it's a complete ion, or whether it's a polar molecule, as well as the distance in between the particles. So for this equation that you see on the right, this is a rendition of Coulomb's law, looking at the force of interaction as a function of the charges and as a function of the distance between those charges. And for each type of interaction, what we see is whether we have an ion or a polar molecule or a nonpolar molecule, that will dictate the exact nature of the relationship. And experimentally, we can use the melting points and the boiling points in order to predict the strength of intermolecular forces. In other words, high melting points or high boiling points is due to high intermolecular forces. There are 7 types of intermolecular forces that we're going to talk about. We have ion-ion intermolecular forces. This is also known as an ionic bond. And we've already discussed this in the context of Coulomb's law. If we have an ion interacting with a polar molecule, we can have ion-dipole interactions. If you have an ion interacting with a non-polar molecule, then we have an ion-induced dipole. All of those interactions require having at least one ion interacting with another species. Then we have what are called the van der Waals forces. The van der Waals forces are interactions that exist between molecules that are not charged. So we could have 2 polar molecules interacting with each other. Because each polar molecule has a dipole, we refer to this as dipole-dipole interaction. Next, we have London dispersion forces, sometimes also just called dispersion forces. And these are when you have non-polar molecules interacting with each other. And then finally, we have dipole-induced dipole. That would be a polar molecule interacting with a non-polar molecule. And then hydrogen bonding. This is a strong interaction of dipole-dipole. And it requires a specific set of elements involved in order to form hydrogen bonds. We'll talk more about each of these in depth. It's important in this overview to recognize that the effects of intermolecular forces are additive. The overall strength of intermolecular forces is going to depend on all intermolecular force types that are present. So you can have cases where you have ion-ion and ion-dipole and ion-induced dipole all in one system. So intermolecular forces are important because this is what dictates how the molecules in our bodies function. For example, DNA and proteins interact with each other through lots of different types of interactions. We see here, these are ion-dipole interactions. And we can have ion-ion interactions involving two different ions. We've seen this already when dealing with Coulomb's law. We know that they're dependent upon the charge of the ions and then the distance between those ions. But we can also have ion-dipole interactions, where these depend on the charge of an ion, as well as the dipole moment, or the degree to which a molecule is polar, and then the distance between those species. We see some examples of this here. We can have a potassium ion interacting with a water molecule. And notice the orientation. The potassium ion is interacting with the oxygen, and that's because oxygen has a partial negative charge. Here is another way of depicting this same scenario, where the potassium ion is being surrounded by a variety of water molecules. Ion-ion interactions occur often within living systems. So this is a protein interacting with DNA. We can see that the protein has a positive charge on the nitrogen, and the DNA has a negative charge on the oxygen for this phosphate. Those interactions are part of what stabilizes the interaction between the protein and the DNA, which allows them to perform their functions. We also have ion-dipole interactions within living systems. We have a protein with an amino acid. This amino acid is lysine. It has a positive charge on the nitrogen, and it's interacting with DNA, and the partial negative charges on oxygen and nitrogen within this DNA molecule. Again, this is stabilizing the interaction between the protein molecule and DNA. Next, we want to talk about dipole-dipole interactions. In order to have a dipole-dipole interaction, you need to have two polar molecules. Remember, we talked about polar molecules as having a dipole moment. Therefore, when those dipole moments align with each other, the two different molecules interact. So dipole-dipole forces are dependent on the strength of the dipole moment. The more polar the molecules, the higher the dipole-dipole interactions. They are also dependent upon the distance. So when molecules are closer together, there's a stronger interaction between them than when they're farther apart. And then finally, the orientation also matters. In this example up here on the top left, we see that the molecules are aligned tail to tail, and the negative end is aligning with the positive end. You'll notice in more complex systems, we do get some alignment like that, but it's not always perfect. So if we get head-on alignment, perfect alignment between the dipoles themselves, then that allows us for a more strong interaction. All right, let's see what you have learned here. I'd like you to pause the video and try this problem on your own, and then I will walk you through it after that. Welcome back. So we want to determine what types of intermolecular forces are present if we have calcium chloride dissolving in ethanol. So what do you need to do to solve this problem? Well, we need to identify what types of species we have. Calcium chloride consists of a metal bound to a nonmetal. Therefore, it is an ionic compound. Ethanol, when you draw out its Lewis structure, you should recognize that ethanol is polar, with a partial negative charge on the oxygen and a partial positive charge on the carbon it's bound to, as well as the hydrogen. So we have ions in solution, and we have polar molecules, and therefore dipoles in the solution, and each of those can interact with any species near it. So we have ions interacting with ions. We have ions interacting with dipoles, and then we have dipoles interacting with dipoles as well. And we will soon see that there's actually more types of intermolecular interactions that are occurring, but we'll get to that in a future video. Thanks for watching, and have a great day.